In this video, we're going to talk about Zener diode. So what is Zener diode? So Zener diode is a special type of diode designed to reliably allow current to flow backwards. So the key word here is backward. Now, when certain set reverse voltage known as the zero break voltage is reached, okay, so that's the definition. Now, in this video, we'll explore several solve problems that will help us to understand the characteristics and some application of Zener diode. So let's first get to the first problem here. Now, for the circuit shown here, we are going to calculate the output voltage, and secondly, then we calculate the voltage drop across series resistance. Then lastly, we will calculate the current through Zener diode. So now let's get to the problem. So let's look at the solution. So if we remove the Zener diode in this figure or this picture that we have here or this diagram, now the voltage V across the open circuit will be given by, we will have V be equal to RL then EI divided by R plus RL. So we know that RL is equal to 10. Then we know that EI is equal to 120. Okay. And we know that R is equal to 5. Right. So if we have this, now let's calculate the V. So the voltage here will be equal to V equal to 10 times 120 over 5 plus 10. Okay, so now we have this. So we have this. So when we do this, we should get 80 volts. Right. Now, since the voltage across the Zener diode is greater than VZ into bracket, which is equal to 50 volts, the Zener is in the on state. So it can be therefore be represented by a battery of 50 volts. Okay, so let's redraw the diagram again. So to redraw the diagram, we will have something like this. Here will be negative and here will be positive. So we have 120 volt here. Then we have R to be 5 kilo ohms. Then we have our I here. We have our IL here. Then we have our 10 kilo ohms. So this is what we are going to get. Then we can replace that with 50 volts. That's the battery. Right. Now, so with our first question, the output voltage. So with our output voltage, we should be getting our output voltage, which is represented by VZ, will be equal to 50 volts. Right. So our second question, which is the voltage drop across the resistance, which is R. So voltage drop across R will be equal to the input voltage minus the output voltage, which is the VZ. So we have 120 minus 50, which when we do that, we should get 70 volts. All right. Now our third question here. The load current. Okay, the load current. So first of all, let's look at the load current. So the load current, which is IL, will be equal to the output voltage divided by the resistance load, or the load resistance, which will be equal to 50 volts divided by 10 kilo ohms. So when we do that, we should get 5 milliampere. All right. So when we should get this, we should be able to calculate for the current through Ri. So current through Ri, which will be equal to 70 volts divided by 5 kilo ohms, which will be equal to 14 milliampere. All right. So now after getting the, we can apply the Kirchhoff's first law. So here, let's apply the first. So applying Kirchhoff's first law, which is I be equal to IL plus IZ. Right. So Zener current, which is IZ, will be equal to I minus IL, which when we do it, we should get 14 minus 5. Then the answer should be 9 milliampere. So it's very, very simple to do. It's very simple to do. Now let's look at the second problem. So in this second problem, for the circuit shown, we are going to find the maximum and minimum values of Zener diode current. Okay, now the first step is to determine the state of Zener diode. It is easy to see that for the given range of voltage, which is the 80 minus 120 volt, the voltage across the Zener is greater than the VZ, which is 50 volts. Okay, so hence what we are going to do here is that the Zener diode will be in the on state for this range of applied voltage. So consequently, it can be replaced by a battery of 50 volts as shown, okay, as shown in this picture. Right. Now, to calculate the maximum Zener current, so let's look at the first one. So maximum Zener current. So the Zener will conduct maximum current when the input voltage maximum, that is 120, under this condition that I'm going to write down. So the first one is voltage across 5 kilo ohms will be equal to 120 minus 50 will be 70 volts. Now current through the 5 kilo ohms will be equal to the 70 volts divided by 5 kilo ohms, which will be 14 milliampere. All right, now let's look at the load current. So the load current, which is IL will be equal to 50 volts divided by 10 kilo ohms. Then we will have 5 milliampere. Right. So when we are done with this, we have current and we have resistance, we have voltage, right? So we can apply the Kirchhoff's law, first law, to find the current, right? The Zener current. So applying Kirchhoff's first law, I will be equal to IL plus IZ. So IZ will be equal to I minus IL. Then we have IZ to be equal to 14 minus 5. Then IZ will be equal to 9 milliampere. 9 milliampere. So what will be the minimum Zener current here? Let's find out and see. Minimum So for the minimum Zener current, the Zener will conduct minimum current when the input voltage, which is the 80 volt, will fall under this condition. So we will have voltage across 5 kilo ohms will be equal to 80 minus 50, which will be equal to 30 volts. Then we'll have current through the 5 kilo ohms, which will be the I, 30 volts divided by the 5 kilo ohms. And that will give us 6 milliampere. Then the load current, which is IL, will be equal to 5 milliampere. Then finally the Zener current, we apply the first law of Kirchhoff's, or Kirchhoff's first law, I minus IL, which will have 6 minus 5, then we'll have 1 milliampere, right? Then we have this. So that will be the minimum current, right? Let's look at the last question for this video. So in this situation here, we have 7.2 volt Zener is used in the circuit shown in this picture, and the load current is to vary from 12 to 100 milliampere. Now we are going to find the value of series resistance R to maintain a voltage of 7.2 volt across the load. So the input voltage is constant at 12 volts and the minimum Zener current is 10 milliampere. So to calculate this here, we will have E. So let's first, the voltage across the R is to remain constant at 12. So let's put this condition down first. So the voltage across R is to remain constant. So it should remain constant at 12 minus 7.2, which will be 4.8 volts, as the load current changes from 12 to 100. Okay, now so the minimum Zener current will occur when the load current is maximum, right? So therefore we will have R to be equal to E I minus E naught, right? Then we will have IZ, right, which is the minimum one, plus IL, which is the maximum, right? So with this we will have 12 volts minus 7.2 volts divided by 100, 10 plus 100 milliampere. Then we'll get total of 43.5 ampere. Okay, so if R here is, we know that if R here is 43.5 ampere is inserted in the circuit, the output voltage will remain constant over the regulating range. So as the load current, which is the IL, decreases, the Zener current IZ will increase to such value that the IL plus the IZ will be equal to 110 milliampere. Okay, and one thing that you have to note is that if the load resistance is open circuited, then the IL will be equal to 0, and the Zener current becomes 110 milliampere. All right, so that is the question for this one, and we are gonna end this video here for now, and I'll meet you in my second video, which is the part 2 of this Zener diode. We are gonna solve more problem for that. Thank you for watching. See you.